Hello everyone, welcome back to the AI Academy, course on building NLP application using HuggingFace Transformer. In this lecture we will discuss about the anatomy of transformers and its key components and functions in detail. So, stay tuned and let's proceed with the lecture. Alright, to truly appreciate transformers, we need to take a step back and look at the history of neural network architectures in natural language processing, NLP. Before transformers, the NLP landscape was dominated by recurrent neural networks, RNNs, and their variants, like long short-term memory, LSTM, and gated recurrent unit, GRU, networks. These models were groundbreaking because they could handle sequential data and capture dependencies over time. However, they had significant limitations. RNNs process sequences step by step, which makes training slow and computationally expensive. They also struggled with long-range dependencies, where the relevant information was far back in the sequence. In 2017, the landscape of NLP changed dramatically with the introduction of the transformer model by Vaswani et al. In their paper, "Attention is All You Need." This new architecture discarded recurrence entirely and relied solely on a mechanism called attention. This shift allowed for parallel processing of sequence data, leading to significant improvements in training efficiency and performance on various NLP tasks. Now, let's break down the key differences between transformers and the previous architectures like RNNs and convolutional neural networks, CNNs. RNNs process data sequentially, one step at a time, which means they can't take full advantage of modern hardware optimized for parallel processing. This makes training slower. Whereas the transformers process all words in a sequence simultaneously, thanks to the self-attention mechanism. This parallel processing speeds up training significantly. The RNNs struggle with capturing dependencies when the relevant information is far apart in the sequence. This is due to the vanishing gradient problem. Whereas the transformers use self-attention to directly connect every word in a sequence to every other word, regardless of their distance. This allows them to capture long-range dependencies more effectively. The RNNs have a simpler architecture with a focus on sequential data, but they require mechanisms like LSTM and GRU units to handle long-term dependencies. Whereas the transformers have a more complex architecture with multiple layers of self-attention and feed-forward networks. This complexity allows them to learn more nuanced representations of the data. The RNNs often incorporate attention mechanisms as an add-on to improve performance. Whereas the transformers place attention at the core of their architecture. The self-attention mechanism is the fundamental building block, enabling the model to weigh the importance of different words in a sequence. The introduction of transformers has had a profound impact on the field of NLP. The transformers have set new benchmarks for a wide range of NLP tasks, including translation, summarization, question answering, and text classification. Models like BERT, GPT, and T5, built on transformer architecture, consistently achieve state-of-the-art results. The transformers have popularized the use of transfer learning in NLP. Pre-trained models like BERT and GPT-3 can be fine-tuned on specific tasks with relatively small amounts of data, making it easier to develop high-performing NLP applications. The flexibility of transformers allows them to be applied to various tasks beyond traditional NLP, such as image processing, like vision transformers or VITs, speech recognition, and even game playing. By enabling parallel processing and reducing the need for sequential operations, transformers have made it feasible to train very large models on massive datasets. This efficiency is crucial for handling the growing scale of data in today's AI applications. The transformer architecture has sparked a wave of innovation and research. Variants and improvements, such as BERT for masked language modeling and GPT for autoregressive generation, have led to continuous advancements in the field. In summary, transformers represent a paradigm shift in how we approach NLP. Their ability to handle large-scale data efficiently, capture complex dependencies, and generalize across tasks has made them a cornerstone of modern AI research and applications. As we continue to explore their capabilities, we can expect even more groundbreaking developments in the future. We will discuss about the basic structure of a transformer. Let's start with the basics of the transformer model's architecture. Transformers follow an encoder-decoder structure, which is a powerful framework for many NLP tasks, such as translation, summarization, and more. Here's a breakdown. The encoder's job is to process the input data, for example, a sentence in English, and transform it into a set of continuous representations. It consists of multiple layers, each containing two main sublayers, a multi-head self-attention mechanism and a position-wise fully connected feed-forward network. The encoder processes the input data in parallel and outputs a sequence of vectors. The decoder's role is to take the encoder's output and generate the desired output, for example, a sentence in French. Similar to the encoder, the decoder has multiple layers with two main sublayers, a multi-head self-attention mechanism and a feed-forward network. Additionally, each decoder layer has a third sublayer that performs multi-head attention over the encoder's output. The decoder's self-attention sublayer is masked to ensure that the prediction for a particular position depends only on the known outputs at positions before it. Now, let's dive into the specific components that make up the transformer model. The first one is multi-head self-attention mechanism. The self-attention mechanism allows the model to weigh the importance of different words in a sequence relative to each other. It computes attention scores for each pair of words, producing a weighted sum of the values. This helps the model focus on relevant parts of the input sequence. And the multi-head attention, instead of performing a single attention function, the transformer uses multiple attention heads. Each head independently learns different attention patterns, providing multiple perspectives and enhancing the model's ability to capture complex relationships. The second component is feed-forward networks, where each layer in the encoder and decoder has a fully connected feed-forward network applied to each position separately and identically. These networks consist of two linear transformations with a ReLU activation in between. They help in transforming the attention outputs into more useful representations. The third component is positional encoding. Since transformers do not have a built-in sense of the order of the words, like RNNs do, they use positional encodings to incorporate the order information. These encodings are added to the input embeddings at the bottoms of the encoder and decoder stacks. They use sine and cosine functions of different frequencies. And the last component is the layer normalization and residual connections. To stabilize and accelerate training, transformers use layer normalization and residual connections around each sublayer. This means the input to each sublayer is added to its output, and then the result is normalized. This helps in preventing vanishing or exploding gradients. Let's now put it all together and understand high-level workflow of the transformers. The input text is tokenized and converted into embeddings, in other words like a set in form of dictionary, which are continuous vector representations. Positional encodings are added to these embeddings to provide information about the position of each token in the sequence. In simple words, embeddings in NLP is a way to represent words or phrases as numbers, which makes it easier for computers to process and understand text. Imagine you have a dictionary with every word in your language. Each word in the dictionary gets a unique address. Similarly, embedding gives each word a unique address but in a multidimensional space. These addresses, or vectors, capture the meaning of words in a way that words with similar meanings are close to each other. High-level workflow of transformers. Think of input embedding as turning words into meaningful numbers. For example, the word cat is converted into a list of numbers that capture its meaning. And the positional encoding, since the order of words matters, such as cat eats fish, is different from fish eats cat, the positional encoding adds information about the position of each word in the sentence. The encoded input, words turned into numbers with positional info, goes through several encoder layers. Each encoder layer applies two main operations. First one is multi-head self-attention. This helps the model look at different parts of the sentence simultaneously and understand relationships between words. And the feed-forward network, this is like a mini neural network that processes the information further. At each step, there are also residual connections, which help in preserving information, and layer normalization, which helps in stabilizing the training, are present. After all encoder layers, the output is a set of vectors. These vectors are the enhanced versions of the original input embeddings, containing rich contextual information about the words. Also, masked multi-head self-attention is a key component in the decoder of a transformer model. Let's break down what it does in simple terms. The self-attention allows the model to look at different parts of a sentence, or sequence, simultaneously to understand the relationships between words. For example, in the sentence, "The cat sat on the mat," self-attention helps the model understand that cat is the one doing the sitting, and mat is where the cat is sitting. And the multi-head aspect means that the model doesn't just look at one aspect of the relationships but several. Imagine having multiple sets of eyes looking at the sentence from different perspectives. Each head in multi-head attention looks at the sentence in a slightly different way, capturing different kinds of relationships between words. These different views are then combined to get a richer understanding. Why we need masking? In the decoder, the goal is often to generate text word by word. When generating a word, the model should only consider the words that have already been generated and not peek at the future words, since they haven't been generated yet. This is where masking comes in. Masking hides the future words from the model. It ensures that when the model is predicting the next word, it can only see the words before it and not the ones that come after. This prevents the model from cheating by looking ahead and ensures it generates words sequentially, just like humans do when writing. Imagine we are generating the sentence, "The cat Saturday." When generating cat, the model can only see the word the. When generating sat, the model can see the cat, but not any words that come after Saturday. Here's a simplified way to visualize masked self-attention. Input: the cat sat. Step 1, generate the attention, the. Step 2, generate cat. Attention, the cat, mask hides sat. Step 3, generate sat. Attention, the cat sat, no mask needed for the last word. In each step, the attention mechanism focuses only on the words generated so far, with future words masked out. How it works in the model. Creating attention scores, for each word in the sequence, calculate attention scores with all other words. This determines how much focus, or attention, each word should give to every other word. Apply a mask to these scores so that any score corresponding to a future word is set to a very low value, effectively, infinity. This ensures that these future words do not influence the current word being generated. Use the masked scores to combine the word representations, focusing only on the relevant words, such as those that have been generated already. By using masked multi-head self-attention, the model can generate text sequentially, considering only the past and present words and ensuring that future words do not influence the current word generation process. This approach is crucial for tasks like text generation and language modeling, where the goal is to produce coherent and contextually accurate sequences. Next, we will look into the feed-forward network, FFN. A feed-forward network is a basic building block in neural networks. Think of it as a mini calculator that processes input data to produce an output. In the context of transformers, after the attention mechanism has processed the relationships between words in a sentence, the feed-forward network takes this processed information and refines it further. It transforms the information through a series of simple mathematical operations, making the data more useful for the next steps. Typically, a feed-forward network in transformers consists of two layers with a nonlinear activation function in between of them. This allows the network to learn and represent complex patterns in the data. Let us now discuss about residual connections and layer normalization. The shortcut paths, think of residual connections as shortcuts. They allow the original input to bypass the feed-forward network and be added to the network's output. This helps prevent the problem of information loss as the data passes through many layers. It ensures that the original information is always available to the model. By providing these shortcuts, the model can learn more effectively. If a layer doesn't improve the performance, the model can skip it, which makes training faster and more stable. We will now look into layer normalization. The layer normalization is like a balancing act. It ensures that the data going through the network remains stable and well-behaved. It adjusts and scales the inputs to each layer so that they maintain a consistent scale and distribution. This prevents issues where some values become too large or too small, which can disrupt learning. By normalizing the inputs at each step, the model can train more efficiently and perform consistently better. How it all fits together. After attention, once the attention mechanism has processed the input and identified important relationships, the data goes through the feed-forward network. Feed-forward network, this network refines and transforms the data, helping the model learn complex patterns. In the residual connections, the original data is added back into the output of the feed-forward network, ensuring no information is lost. And in the layer normalization, the data is normalized to keep it stable and well-behaved, ensuring effective learning. In summary, the feed-forward operations is like, think of these as mini calculators that further process and refine the information after attention has been applied. The residual connections are the shortcuts that help retain the original information and make learning easier and more effective. And the layer normalization is the balancing act that keeps the data stable and well-scaled, ensuring consistent and efficient training. Together, these components ensure that each layer in a transformer model processes the input data effectively, retains important information, and remains stable during training, leading to better performance and faster learning. Next is producing the output sequence. The final steps in the decoder. After the decoder has processed all the input information, it produces a final output. This output is still in the form of complex numbers and needs to be converted into actual words. The linear layer for converting to vocabulary size. The final output goes through a linear layer. Think of this as a translator that converts the output into a list of numbers, where each number corresponds to a word in our vocabulary. This list has the same size as the total number of words the model knows, its vocabulary. In the softmax function, this list of numbers goes through a softmax function. This function converts the numbers into probabilities, which indicate how likely each word in the vocabulary is the next word in the sequence. Imagine you have a list of words with scores next to them. The softmax function turns these scores into percentages that add up to 100%, representing the likelihood of each word. The model then picks the word with the highest probability, the word most likely to be correct, as the next word in the sequence. For example, if the probabilities are highest for the word apple, the model chooses apple as the next word. This process repeats for each word in the output sequence. After choosing apple, the model uses it as part of the input for predicting the next word. It continues this way, word by word, until the entire sentence or output sequence is generated. In summary, the linear layer converts the decoder's output into a list of numbers, each representing a possible word in the vocabulary. The softmax function changes these numbers into probabilities, showing how likely each word is to be the next one. The model picks the word with the highest probability as the next word in the sequence. This process continues until the entire output sequence is generated, creating the final sentence or text. By using the linear layer and softmax function, the transformer model can effectively translate complex outputs into actual words, building a coherent sentences one word at a time. Let us now discuss about the training and inference. The training is a process where the model learns to do its job, for example translating sentences or classifying text. The model makes a guess about what the output should be for a given input. This guess is compared to the actual correct output. If the guess is wrong, the model makes a note of this mistake. The model has many adjustable settings called parameters. When it makes mistakes, it adjusts these parameters slightly to improve its future guesses. This process is repeated many times with lots of examples, so the model gradually gets better and better at making accurate predictions. Next, we will discuss about the inference. The inference is the phase where the model uses what it learned during training to make predictions or generate text. Now that the model is trained, it can take a new input, like a sentence to translate, and produce an output, the translated sentence. Then comes generating text step by step. When generating text, the model predicts one word at a time. It starts with the first word, then uses this word as part of the input to predict the next word. This continues with each new word being added to the input to predict the following word, until the whole sentence is generated. In summary, the model learns by comparing its guesses to the correct answers and adjusting its settings to reduce mistakes. This helps the model improve over time by learning from lots of examples. Once trained, the model can use its knowledge to make predictions or generate text. It generates text one word at a time, using previously predicted words to help predict the next ones. By understanding training and inference, we see how the model learns from examples and then uses this learning to perform tasks like translating sentences or generating text accurately. In summary, transformers use a sophisticated architecture involving layers of attention mechanisms and feed-forward networks to process and generate sequences of text. This allows them to understand and produce human language in a very effective way. Let us now discuss the detailed anatomy of the encoder. The encoder in a transformer model is a sophisticated component designed to process the input sequence and transform it into a rich set of continuous representations. Let's break down its structure and functions in detail. The input embedding and positional encoding, where each word or token in the input sequence is first converted into an embedding, a dense vector representation that captures its meaning. And the positional encodings are then added to these embeddings to incorporate the position of each token in the sequence, allowing the model to understand the order of the words. The encoder consists of a stack of identical layers, typically between 6 to 12 layers, each comprising two main sublayers, a multi-head self-attention mechanism and a position-wise feed-forward network. The multi-head self-attention mechanism is a core component of the encoder. Here's how it works. The self-attention allows the model to weigh the importance of different words in a sequence relative to each other. For each word, it computes a weighted sum of the other words, focusing on the relevant ones. And this is achieved by creating three vectors from each input embedding, a query vector, Q, a key vector, K, and a value vector, V. These vectors are generated through learned linear transformations. The attention score between two words is calculated using the dot product of their query and key vectors, scaled by the square root of the dimension of the key vectors. This score indicates how much focus one word should have on another. Each word's final representation is computed as the weighted sum of the value vectors, using the attention probabilities as weights. This allows the model to emphasize the most relevant words in the context of each word. Next, instead of performing a single attention operation, the transformer uses multiple heads, such as 8 or 12 heads. Each head independently learns different attention patterns, providing multiple perspectives. The outputs of all heads are concatenated and linearly transformed to form the final representation. After the multi-head self-attention sublayer, the output is passed through a position-wise feed-forward network, which is the second sublayer in each encoder layer. Here's how it functions. The feed-forward network consists of two fully connected linear layers with a ReLU activation function in between. The first linear layer projects the input to a higher dimensional space, while the second linear layer projects it back to the original dimension. And the element-wise operations are applied to each position in the sequence independently and identically. This means the same feed-forward network is used for each word, allowing for consistent transformations. Next, we will discuss about the layer normalization and residual connections to ensure stable and efficient training. Each sublayer in the encoder layer includes residual connections and layer normalization. A residual connection, also known as a skip connection, adds the input of a sublayer to its output. This helps in preserving the original information and aids in backpropagation, preventing the vanishing gradient problem. After the residual connection, layer normalization is applied to the output. This normalizes the activations, ensuring that they have a mean of 0 and a variance of 1. This step is crucial for stable training and faster convergence. In summary, the encoder in a transformer model is a powerful and complex structure designed to process and understand the input sequence. Its combination of multi-head self-attention mechanisms, position-wise feed-forward networks, residual connections, and layer normalization allows it to capture intricate relationships and dependencies within the data. This makes the encoder an essential component for transforming input data into meaningful representations that can be used for various NLP tasks. Next, we will move on to detailed anatomy of the decoder. The decoder in a transformer model is designed to generate the output sequence from the encoded input sequence. It mirrors the encoder in many ways but has additional mechanisms to handle the generation task. So, like the encoder, the decoder begins by converting each token in the target sequence into embeddings and adding positional encodings to capture the order of the tokens. The decoder consists of a stack of identical layers, typically between 6 to 12, each comprising 3 main sublayers: a masked multi-head self-attention mechanism, an encoder-decoder attention mechanism, and a position-wise feed-forward network. The masked multi-head self-attention mechanism is crucial for autoregressive generation tasks, ensuring that the model only attends to past tokens when predicting the next one. In the decoder, self-attention is masked to prevent the model from seeing future tokens in the sequence. This is achieved by applying a mask to the attention scores, setting the scores of future tokens to -infinity before the softmax operation. This ensures that the prediction for a specific position depends only on the known outputs up to that position. And as with the encoder, the decoder uses multiple attention heads to learn different representations and attention patterns. The outputs of all heads are concatenated and linearly transformed to form the final representation for each position. The encoder-decoder attention mechanism allows the decoder to focus on relevant parts of the input sequence, encoded by the encoder, while generating the output sequence. Each decoder layer includes an encoder-decoder attention sublayer. This sublayer performs multi-head attention over the encoder's output, using it as the key and value while the decoder's previous layer output serves as the query. This mechanism enables the decoder to align the generated tokens with the input sequence, effectively learning which parts of the input are important for producing each token in the output. Similar to other attention mechanisms, multiple heads are used here to capture various alignment patterns between the input and output sequences. The outputs from all heads are concatenated and linearly transformed. After the attention mechanisms, the output is processed through position-wise feed-forward networks, identical to those in the encoder. The feed-forward network consists of 2 fully connected linear layers with a ReLU activation in between. The first layer projects the input to a higher dimensional space, and the second layer projects it back to the original dimension. These operations are applied independently and identically to each position in the sequence, allowing for consistent transformations across all positions. To ensure stable and efficient training, each sublayer in the decoder layer includes residual connections and layer normalization. The residual connections, or skip connections, add the input of a sublayer to its output. This helps preserve the original information and aids in backpropagation, preventing the vanishing gradient problem. And the layer normalization is applied after the residual connection. This normalizes the activations to have a mean of 0 and a variance of 1, ensuring stable training and faster convergence. In summary, the decoder in a transformer model is a sophisticated component designed to generate output sequences effectively. Its combination with the masked multi-head self-attention mechanisms, encoder-decoder attention mechanisms, the position-wise feed-forward networks, the residual connections, and the layer normalization allows to capture complex dependencies and alignments within the data. This makes the decoder a vital part of the transformer model for tasks like translation, summarization, and other sequence generation applications. Let us now understand the self-attention. To know the power of transformers, it's essential to understand the concept of self-attention. Self-attention is a mechanism that enables the model to weigh the importance of different words in a sentence relative to each other. Imagine you're reading a sentence and you want to understand the meaning of a particular word. Naturally, you look at other words in the sentence to gather context. Self-attention mimics this behavior by allowing the model to focus on different parts of the input sentence when processing each word. In traditional models like RNNs, each word's representation primarily depends on the previous words in the sequence. However, self-attention allows each word to be directly connected to every other word, regardless of their position. This direct connection enables the model to better capture relationships and dependencies in the data, even if they are far apart in the sequence. The self-attention mechanism involves several steps to calculate how much focus one word should have on another. For each word in the input sequence, we create three vectors: a query vector, Q, a key vector, K, and a value vector, V. These vectors are obtained by multiplying the input embedding by learned weight matrices. The query and key vectors help determine the attention scores, while the value vectors contribute to the final output. The attention score between two words is calculated using the dot product of their query and key vectors. This score represents how much attention one word should pay to another. To ensure the dot products don't get too large, especially when the dimensionality of the vectors is high, we scale the scores by the square root of the dimension of the key vectors. This scaling step helps stabilize the gradients during training. The scaled attention scores are then passed through a softmax function to convert them into probabilities. This ensures that the attention weights for each word sum up to 1. And the softmax function highlights the most relevant words by assigning them higher probabilities. The final output for each word is computed as the weighted sum of the value vectors, using the attention weights as weights. And this step produces a new representation for each word, enriched by the context from the entire sequence. Let's delve a bit deeper into the scaling and softmax operations. In the softmax operations, the scaling factor is crucial because the dot product of high-dimensional vectors can result in very large values, leading to extremely small gradients during backpropagation. By scaling the scores, we keep the values in a manageable range, facilitating stable training. The softmax function transforms the scaled scores into a probability distribution. This normalization ensures that the sum of the attention weights for each word equals 1, making it easier for the model to focus on the most relevant parts of the sequence. In summary, the self-attention mechanism allows the transformer model to weigh the importance of different words in a sequence relative to each other. By calculating attention scores, scaling them, and applying the softmax function, the model can generate new representations for each word that incorporate context from the entire sequence. This powerful mechanism enables transformers to excel at capturing complex relationships and dependencies in data, leading to their success in various NLP tasks. Let us now discuss about multi-head self-attention in detail, to understand why multi-head attention is a key component of the transformer model. The purpose of using multi-headed attention feature is that it allows the model to focus on different parts of the input sequence simultaneously. Each attention head can learn to capture different types of relationships and patterns in the data. By having multiple heads, the model increases its capacity to represent the data. This helps in capturing more nuanced and complex features that a single-head attention mechanism might miss. And also, multi-head attention facilitates parallel processing, which is crucial for leveraging modern hardware and improving computational efficiency. The benefits are that with multiple heads, the model can learn various aspects of the data, such as syntactic structure, semantic meaning, and long-range dependencies, all at the same time. The different heads can focus on different parts of the sequence, making the model more robust to noise and variations in the data. And by capturing diverse patterns, multi-head attention helps the model generalize better to unseen data, improving overall performance on various NLP tasks. The main operations of the multi-headed attention feature are like splitting the queries, keys, and values. In the multi-head attention mechanism, each attention head operates on a subset of the input data. Here's how the splitting process works. The initial linear transformations, in which the input embeddings for each word in the sequence are first transformed using learned weight matrices to generate the query, Q, key, K, and value, V, vectors. Next, the query, key, and value vectors are then split into multiple smaller vectors, one for each attention head. This splitting allows each head to operate on a reduced dimensional subspace, ensuring that different heads can focus on different aspects of the data. Each head performs the attention mechanism independently on its subset of query, key, and value vectors. This involves calculating attention scores, scaling, applying the softmax function, and computing the weighted sum of values for each head. Let us now discuss about the concatenation and projection in multi-head attention. After each attention head has processed its subset of the data, the outputs need to be combined to form the final multi-head attention output. Here's how this is done. The concatenation: imagine you have multiple teams working on different parts of a project. Each team produces a part of the final report, output. When all teams are done, you gather their individual reports and put them together into one big report. This step of gathering and combining the individual reports is called concatenation. And the linear projection: after concatenation, the combined report needs to be polished and refined into a final format. This step involves passing the combined report through a linear transformation using a learned weight matrix. Think of this as a final editing process that ensures the report is well organized and in the right format. This transformation helps in combining the information from all teams into a cohesive and well-structured final report that is ready for the next stages of processing in the transformer model. In summary, multi-head attention enhances the transformer model's ability to learn diverse and complex representations by allowing multiple attention mechanisms to operate in parallel on different subsets of the data. The process involves splitting the query, key, and value vectors, and independently calculating attention for each head, concatenating the outputs from all heads, and projecting the concatenated output back to the original input dimension. This multifaceted approach provides a robust and expressive mechanism for capturing intricate patterns and dependencies within the input sequence, contributing to the transformer's success in various NLP tasks. Next, let us now understand the role of positional encoding in transformers. The transformers revolutionized NLP by leveraging self-attention mechanisms, which excel at capturing relationships between words in a sequence. However, one critical challenge with self-attention is that it treats the input sequence as a bag of words, ignoring the order of the words. This is where positional encoding comes into play. Incorporating the sequence order, unlike RNNs, which inherently process sequences in order, transformers process all tokens simultaneously. Positional encoding provides the model with information about the order of tokens in the sequence. Understanding the order is essential for capturing the syntactic and semantic structure of the language. For example, in the sentence "the cat sat on the mat," the positions of cat and mat determine the meaning. The positional encodings are added to the input embeddings to give the model a sense of position. These encodings are vectors of the same dimension as the embeddings, ensuring that the positional information is integrated seamlessly with the token representations. This integration allows the model to distinguish between different positional contexts, enabling it to understand dependencies and relationships based on word order. Let us now understand the difference between learned and fixed positional encodings. So, there are two primary approaches to incorporating positional information into the transformer model: learned positional encodings and fixed positional encodings. Let's explore the differences between them. In the fixed positional encodings, the fixed positional encodings are generated using sinusoidal functions of different frequencies. The idea is to create a unique encoding for each position in the sequence. They do not require learning parameters, reducing the model's complexity. The same positional encoding is used across different sequences and models, providing a consistent method for encoding positional information. The use of sinusoidal functions allows the model to potentially generalize to longer sequences than those seen during training. Whereas in the learned positional encodings, the positional encodings are treated as learnable parameters. Each position in the sequence has an associated vector that is learned during the training process. These positional embeddings are optimized along with other parameters in the model, adapting to the specific characteristics of the training data. The model can learn to encode positional information in a way that is most beneficial for the task at hand, potentially capturing more complex positional dependencies. Since the positional encodings are learned, they can adapt to the specific structure and patterns of the training data, potentially improving performance on the given task. In summary, positional encoding is a crucial component in transformers, enabling the model to capture the order of words in a sequence, which is vital for understanding context and meaning. Fixed positional encodings, based on sinusoidal functions, offer a predefined and consistent way to incorporate positional information, while learned positional encodings provide flexibility and adaptability by learning from the data. Both approaches have their advantages, and the choice between them can depend on the specific requirements and characteristics of the NLP task at hand. Let's now walk through the sample implementation of fixed positional encodings using sinusoidal functions in Python. We'll create a function that generates positional encodings for a given sequence length and embedding dimension. In this example, first we define a function get_positional_ encodings designed to generate positional encodings for a sequence of tokens. The positional encodings help the transformer model understand the order of tokens in the input sequence since transformers do not inherently have a sense of token position. The function starts by creating a matrix POS_enc filled with zeros. This matrix has dimensions of sequence_len, d_model, where sequence_len is the length of the input sequence, and d_model is the dimensionality of the model or the embedding dimension. Then we compute the positional encodings, so the function then fills in this matrix using sine and cosine functions. It loops through each position POS in the sequence and each dimension I in the embedding. For even indices I, it uses the sine function. And finally, the function returns the filled positional encoding matrix. When we call the function with a sequence length of 10 and a model dimension of 16, it generates a 10 by 16 matrix of positional encodings. The output is a matrix where each row represents the positional encoding for a token in the sequence, and each column represents a dimension of the encoding. In other words, imagine you have a sequence of words, and you want to give each word a sense of its position in the sequence. The getPositionalEncodings function does exactly that by creating a special matrix using sine and cosine math functions. First, it sets up an empty grid matrix with zeros. Next, it fills in the grid with values from sine and cosine functions. These values change based on the position of the word in the sequence and the dimension we are looking at. And finally, it gives you a matrix where each row represents the position of a word in the sequence in a unique way that the transformer model can understand. When you run this code with a sequence length of 10 and a dimension of 16, you get a 10 by 16 grid. Each row of this grid is a unique pattern of numbers that helps the model keep track of the position of each word. In summary, fixed positional encodings using sinusoidal functions provide a robust way to incorporate positional information into transformer models. These encodings ensure that each position in the sequence has a unique representation, allowing the model to understand the order of tokens effectively. The mathematical formulation using sine and cosine functions, along with the implementation in Python, demonstrates how these encodings are generated and utilized in practice. Let us now look into the data preparation and tokenization. Before training a transformer model, it's essential to preprocess the text data to ensure it is in a suitable format for the model. Here are the key steps involved in text preprocessing. The steps involved in the text cleaning are: lowercasing, where we convert all text to lowercase to ensure consistency. And second is removing punctuation and special characters to strip out any unnecessary punctuation and special characters that do not contribute to the meaning. And handling contractions, in which we expand contractions, like don't, is converted to do not, to standardize the text. The next step is normalization, using stemming or lemmatization to reduce the words to their root forms, like running becomes run, to normalize the text. And removing stop words to eliminate common words, like the and, that do not carry significant meaning. The fourth step is tokenization. This involves splitting the text into individual tokens, words or subwords, that the model can process. Tokenization can be done using various techniques. There are several tokenization techniques available to use, each with its own advantages and trade-offs. Like in the byte pair encoding, the BPE algorithm starts with a base vocabulary of individual characters and iteratively merges the most frequent pairs of characters or subwords to create new tokens. This process continues until a predefined vocabulary size is reached. BPE can also handle out-of-vocabulary words by breaking them down into subword units, making it robust for handling rare and unseen words. For example, the word unhappiness might be tokenized as unhappiness after a few iterations. The next is the word piece technique. Similar to BPE, word piece also starts with a base vocabulary of characters and merges subwords based on their likelihood and frequency in the training corpus. It uses a different criterion for merging pairs compared to BPE. The word piece is widely used in models like BERT and provides an effective balance between vocabulary size and the ability to handle rare words. For example, the word playing might be tokenized as play, ##ing, where hashtag indicates that ing is a subword attached to a previous token. Another tokenization technique is the sentence piece. The sentence piece treats the text as a sequence of bytes or Unicode characters, which allows it to handle languages without spaces between words. It uses BPE or Unigram language model to tokenize the text. Sentence piece can handle languages like Chinese and Japanese more effectively, where words are not separated by spaces. For example, the word data might be tokenized as D-A-T-A, or as subwords depending on the trained model. Let us now look into the handling of special tokens and padding. In addition to tokenizing the text, it's important to handle special tokens and padding to ensure the data is in the correct format for the transformer model. CLS. The classification token is used at the beginning of the input sequence in models like BERT for classification tasks. The separator token is used to separate different segments of the input, such as in question answering tasks or sentence pair classification. The mask token is used in masked language modeling tasks where certain tokens are masked and the model predicts them. And the padding token is used to pad sequences to a uniform length for batch processing. The main purpose of the padding is that the transformers process fixed-length sequences, so input sequences must be padded to the same length. Padding ensures that shorter sequences do not affect the batch size and allows for efficient parallel processing. The sequences are padded with a pad token to reach the maximum sequence length in the batch. Attention masks are used to ensure that padding tokens do not influence the model's predictions. For example, if the maximum sequence length is 10, a sequence like the cat, sat, would be padded to the cat, sat, filled with pad up to sequence length 10. Let us now look into some example code for tokenization and padding using the HuggingFace Transformers library. We are using the BERT tokenizer from the HuggingFace Transformers library to process a sample text. The quick brown fox jumps over the lazy dog. We start by initializing the BERT tokenizer and then tokenize the sample text to split the text into individual tokens that the model can understand. Then, we convert these tokens into their corresponding numerical IDs. In the output, each token is mapped to a unique ID that the BERT model uses internally. Next, we add special tokens, CLS, at the beginning, and the SEP, at the end of the sequence to help the model understand the boundaries. The output is the input IDs with special tokens. The sequence now includes CLS, at the start, ID 101, and SEP, at the end, ID 102. Next, we pad the sequence to a fixed length to ensure all input sequences are the same length, which is essential for batching. The output is the padded input IDs. The sequence is already 12 tokens long, so no extra padding is needed. If it were shorter, padding tokens would be added to the end. And then we create an attention mask to indicate which tokens are actual data represented by 1 and which are padding represented by 0. Since there are no padding tokens, the attention mask is all ones, indicating that all tokens are relevant. In this example, we use the BERT tokenizer to process a sentence by tokenizing it, converting tokens to IDs, adding special tokens, padding the sequence, and creating an attention mask. Each step ensures that the input is in the correct format for the BERT model to understand and process. The output at each stage shows the transformation of the text from human-readable words to a format suitable for machine learning models. Next, we will look into the optimizers and learning rate schedulers. The optimizers play a crucial role in training neural networks by adjusting the model's parameters to minimize errors. One of the most popular optimizers used in training transformers is the ADAM optimizer. The ADAM stands for Adaptive Moment Estimation. It combines the benefits of two other optimizers, AdaGrad and RMSProp, to adjust learning rates for each parameter automatically. The key components are the first moment estimate, which tracks the average of the gradients. And the second is the moment estimate, which tracks the average of the squared gradients. ADAM-W is a variant of ADAM that handles weight decay differently. It separates weight decay from the gradient update process, which helps prevent overfitting. Instead of applying weight decay to the gradients, ADAM-W applies it directly to the weights after updating them. And the other variants are AMS-grad. This variant keeps track of the maximum past squared gradients to prevent the learning rate from increasing too quickly. And AdaBound combines the benefits of adaptive learning rates with the stability of traditional methods by capping the learning rates within a certain range. Similarly, the learning rate schedules, such as warm-up and decay, adjusts the learning rate during training to help the model learn more effectively and prevent overfitting. The gradient clipping and regularization help stabilize training and prevent issues such as exploding gradients. The gradient clipping prevents the gradients, which update the model's parameters, from becoming too large, which can destabilize training. The gradients are capped at a maximum value to ensure they stay within a safe range. The regularization techniques are weight decay, that adds a penalty to the loss function based on the size of the model parameters, encouraging smaller weights and helping to prevent overfitting. And the dropout, which randomly sets a portion of the neurons to 0 during training to prevent them from becoming too dependent on each other, which helps the model generalize better to new data. Next, the label smoothing softens the target labels, reducing the model's confidence in its predictions and improving its ability to generalize. Instead of using one-hot encoding where the true label is 1 and others are 0, the true label is assigned a slightly lower value, and a small probability mass is distributed among the other labels. In summary, optimizers like ADAM and its variants, along with learning rate schedules, gradient clipping, and regularization techniques, are essential tools for training effective and stable neural networks. They help models learn more efficiently, prevent overfitting, and ensure stable training. Let us now look into the example code for optimizers and learning rate schedulers. So, here's an example of implementing the ADAM-W optimizer with a linear warm-up and cosine decay schedule using the HuggingFace transformers library. First of all, we are importing necessary libraries from PyTorch and HuggingFace transformers library. These libraries help us load pre-trained models, handle data, and perform optimization. Next, we define a custom dataset class that inherits from PyTorch's dataset class. This class will handle our data, providing methods to get the length of the dataset and retrieve items by index. Then, we create sample data for training and evaluation. Each entry includes input_IDs, attention_mask, and labels. For simplicity, we repeat the same sample 100 times. Next, we wrap our sample data into our custom dataset class and then create data loader objects for both training and evaluation. Data loader helps in batching and shuffling the data. We load a pre-trained BERT model and its tokenizer from the HuggingFace model hub. We set the number of epochs, initialize the AtomW optimizer, calculate the total number of training steps, and define a learning rate scheduler with a warm-up phase. We run the training loop, iterating over the epochs and batches. We perform forward and backward passes, apply gradient clipping, and update the optimizer and scheduler. We print the training progress every 10 steps and handle any potential errors. In the output, this warning informs us that the classifier layer weights are newly initialized, and we should train the model on our specific task. The training loop runs for 3 epochs. During each epoch, the loop iterates over the batches and prints the loss every 10 steps. We see the loss decreasing significantly, indicating that the model is learning and improving. In summary, this code demonstrates how to set up a training loop for a pre-trained BERT model using PyTorch and HuggingFace transformers. It includes data preparation, model loading, optimizer and scheduler setup, and a training loop with error handling and progress monitoring. The output shows the training progress and confirms that the model training is completed. Next, we will be looking into the loss functions. When we are training a transformer model for NLP tasks, selecting the right loss function is crucial for optimizing model performance. Loss functions measure how far off the model's predictions are from the actual targets and guide the optimization process to improve the model. Here are some common loss functions used in NLP tasks. The common loss functions for NLP tasks are cross-entropy loss. This loss function is widely used for classification tasks, where the goal is to predict which category or class an input belongs to. For example, if you're building a model to classify emails as either spam or not spam, you'd use cross-entropy loss. It measures how well the predicted probabilities match the actual labels. The idea is to penalize the model more when it assigns low probabilities to the correct class. Next is mean squared error, MSE. It is used for regression tasks, where the goal is to predict continuous values. For instance, if you're predicting house prices based on various features, you would use MSE. It calculates the average squared difference between the actual and predicted values. Smaller values indicate better performance. The binary cross-entropy, BCE, this is used for binary classification tasks, where there are only 2 possible outcomes, like predicting whether a tweet is positive or negative. It measures the dissimilarity between the actual binary outcome and the predicted probability. The loss increases as the predicted probability diverges from the actual label. And the hinge loss, a commonly used for training classifiers like support vector machines. An example would be a model distinguishing between 2 classes, such as cat versus dog. It focuses on ensuring that the correct class is not just predicted but predicted with a margin. It penalizes predictions that are correct but too close to the decision boundary. Let us now look into the cross-entropy loss for classification tasks. The cross-entropy loss is the most commonly used loss function for classification tasks in NLP, such as text classification, sentiment analysis, and language modeling. It measures how well the predicted probability distribution matches the actual labels. Think of a scenario where you have a model predicting whether a movie review is positive or negative. Cross-entropy loss will compare the model's predicted probabilities with the actual label and penalize more heavily when the correct class has a lower predicted probability. The logits versus probabilities. Logits are the raw scores output by the model before applying a softmax function. They can be any real number. And the probabilities are obtained by applying the softmax function to the logits, turning them into values between 0 and 1 that sum up to 1. Why use logits? As it's often more stable to compute cross-entropy loss directly from logits, as it avoids potential numerical issues with very small or very large probability values. Next, we will be looking into the masking and handling padded tokens in loss computation. When training transformer models, especially with variable length sequences, it's common to pad sequences to a uniform length. However, padded tokens should not contribute to the loss computation, as they are not part of the actual data. Masking is used to handle these padded tokens. Padding and masks: the sequences are padded with a special token, such as pad, to ensure uniform length. And the attention masks, also known as binary masks, indicating which tokens are real and which are padding. During loss computation, padded tokens should be ignored. This can be achieved by applying the mask to the loss values. The implementation is like compute the loss for each token in the sequence. Apply the mask to zero out the loss values for padded tokens. And compute the mean or sum of the masked loss values for backpropagation. Let us look into an example. In this example, first we are importing the PyTorch library and some of its functions to help with tensor operations and loss calculations. Then we define the example batch of predicted logits and target labels. The logits represent the raw predictions from a model for a batch of 2 examples, each with 3 possible classes. And labels are the true class labels for these 2 examples. Then we create the example attention mask, shape. The attention mask indicates which tokens are real and which are padding. In this case, the first token is real, and the second token is padding. We compute cross-entropy loss for each token. We initialize a cross-entropy loss function without reducing the loss, meaning we get a loss value for each token in the batch. And the loss per token calculates the loss for each example in the batch based on the predicted logits and the true labels. Then we apply the attention mask to the loss. We apply the attention mask to the loss per token. This masks out the loss for padding tokens by multiplying by 0, leaving the loss for real tokens unchanged. Next, we compute the mean loss ignoring padding. So, we calculate the mean loss, ignoring padding tokens, by summing the masked loss and dividing by the sum of the attention mask, which counts the number of real tokens. Finally, we print the mean loss. The mean loss is calculated only for the real tokens, ignoring the padding tokens. Here, the first example in the batch contributes to the loss, and the second example does not, as indicated by the attention mask. The value 0.41 is the average loss for the real tokens in the batch, giving us an idea of how well the model's predictions match the actual labels for these tokens. In this example, we demonstrated how to compute cross-entropy loss for a batch of predictions, apply an attention mask to ignore padding tokens, and calculate the mean loss only for real tokens. This approach is useful when dealing with variable length sequences in NLP tasks, ensuring that padding does not affect the loss calculation and model training. In summary, loss functions play a crucial role in training NLP models. Cross-entropy loss is the most common choice for classification tasks, providing a measure of how well the model's predicted probabilities match the true labels. Proper handling of padded tokens through masking ensures that the loss computation is accurate and reflects only the real tokens in the sequences, leading to better model performance and training stability. Let us now look into the example of fine-tuning pre-trained transformers. Fine-tuning pre-trained transformer models is an effective way to leverage their extensive training on large datasets. By fine-tuning, we adapt a pre-trained model to the specific nuances of our target task. In this step we first install the transformers library using pip install transformers. Next, we load a pre-trained BERT model for sequence classification. In the code below we will demonstrate fine-tuning a pre-trained BERT model for a text classification task. First we prepare the dataset and tokenize the input text. In the next step we create a data loader for batching and shuffling the dataset. Then we set up the training loop with an optimizer and a learning rate scheduler. After training, we evaluate the model on a validation set. The final output of the code provides the accuracy of the model, as 0.5. This means that the model correctly predicted the labels for 50% of the examples in the dataset. In this example, we demonstrated how to fine-tune a pre-trained BERT model for a text classification task. The process involved were 1. Loading a pre-trained model and tokenizer. 2. Preparing the dataset and creating a data loader. 3. Defining the training loop with an optimizer and a learning rate scheduler. 4. Evaluating the model to check its performance. By following these steps, you can adapt pre-trained transformer models to various specific NLP tasks, leveraging their powerful capabilities to achieve good performance on your data. Let us now discuss about the transformer variants and innovations. Since the introduction of the original transformer architecture by Vaswani et al. In 2017, several variants have been developed, each designed to address specific challenges and optimize performance for various NLP tasks. Here are some of the most notable transformer variants. The BERT, the short form of bidirectional encoder representations from transformers. BERT is designed to pre-train deep bidirectional representations by jointly conditioning on both left and right context in all layers. This approach allows BERT to capture context from both directions. The key features are like masked language modeling, also known as MLM, randomly masks tokens in the input sequence and predicts the masked tokens, allowing the model to learn bidirectional context. And the next sentence prediction, also known as NSP, which predicts whether two sentences appear consecutively in the text, helping the model understand sentence relationships. BERT excels at tasks like question answering, text classification, and named entity recognition. Another variant is GPT, which is short form of Generative Pre-trained Transformer. GPT is an autoregressive transformer model that generates text by predicting the next word in a sequence, given the previous words. The key features are like it is unidirectional, it processes text from left to right, focusing on generating coherent and contextually accurate text. GPT is pre-trained on a large corpus and fine-tuned for specific tasks with task-specific data. It is well suited for text generation, dialogue systems, and language modeling. Next one is T5, short form of text-to-text transfer transformer. So the T5 treats every NLP task as a text-to-text problem, converting input text to output text. This unified approach simplifies the training and application of the model across different tasks. The key features are like, it is task agnostic, it converts all tasks into a text-to-text format, enabling a single model to handle multiple NLP tasks. It's pre-trained on the objective of denoising autoencoder approach, where parts of the input are corrupted and the model learns to reconstruct the original text. T5 is versatile and performs well in tasks like translation, summarization, and question answering. Another variant is Roberta, also known as Robustly Optimized BERT approach. The Roberta is a robustly optimized version of BERT, with improvements in training procedures and hyperparameters. The key features are like they are trained on a larger dataset and for more steps than BERT. It uses dynamic masking during training, changing the masked tokens in each epoch. Roberta outperforms BERT in various NLP benchmarks, making it suitable for tasks like sentiment analysis and text classification. And finally, the DistillBERT variant. The DistillBERT is a distilled version of BERT, designed to be smaller, faster, and more efficient while retaining 97% of BERT's performance. The key features are like it is trained using knowledge distillation, where a smaller student model learns from a larger teacher model. The reduced model size and faster inference make it suitable for deployment on resource-constrained devices. DistillBERT is used for tasks like text classification, named entity recognition, and question answering where computational efficiency is crucial. Let us now talk about the continuous innovations and improvements over the original transformer architecture. The original transformer architecture has inspired numerous innovations and improvements to enhance its performance, efficiency, and applicability. Here are some key innovations. The pre-training objectives are like, the masked language modeling, introduced by BERT. The MLM masks random tokens in the input and predicts them, enabling the model to learn bidirectional context. And another is denoising autoencoders. It is used by T5. This approach corrupts parts of the input and trains the model to reconstruct the original text, enhancing its ability to handle noisy data. The training strategies such as dynamic masking employed by Roberta, which changes the masked tokens in each training epoch, providing more robust training. Training on larger datasets for more iterations, as seen with Roberta, leads to improved performance. The model compression was achieved by using knowledge distillation, using techniques like those used in DistillBERT to reduce model size and inference time while retaining the performance. The student model learns from a larger teacher model, making it more efficient. The long-former and the big BERT are models that introduce the sparse attention mechanisms to efficiently handle longer sequences, extending the capabilities of transformers beyond the original sequence length limitations. Introduction of multimodal transformers. The visual BERT and ViolBERT combined the text and visual inputs, enabling the model to handle tasks that require understanding both modalities, such as image captioning and visual question answering. And the fine-tuning techniques like the adapter layers, introduced as lightweight layers added to pre-trained models, allowing efficient fine-tuning for specific tasks without modifying the entire model. And the prefix tuning, it modifies only the prefix of the input sequence during fine-tuning, reducing the number of trainable parameters. Let us now look into the real-world use case example of summarizing a news article. In this section we will cover the basic process with an example of summarizing a news article using the BERT model, including how it fetches a real-world news article and generates a summary using the BERT model. The step-by-step explanation is: One is to import libraries and set up. First, we need to import the necessary libraries and choose a news website and article URL to summarize. From Transformers, import BERT for conditional generation, BERT tokenizer. We import the BERT model and tokenizer from the HuggingFace Transformers library. And from BS4, import Beautiful Soup and import requests are used for web scraping to fetch the content of a news article from a URL. Step 2. We fetch the content of the article from the chosen news URL. We specify the URL of the news article bbc.com/news/world-us-Canada. It's an example URL, you can replace with your desired article. To fetch the article content, we use requests.get to fetch the content from the URL and Beautiful Soup to parse the HTML content. We then extract the article text by finding all paragraph tags with a specific class. We use find_all to get all paragraph tags with the class. We extract the text from these paragraphs and join them into a single string, article_text. Step 3. We load the BERT model and tokenizer to prepare for summarization. We specify the model's name, Facebook/BERT large CNN, and load both the model and tokenizer using from_pretrained. We tokenize the article text to convert it into a format that the model can process. The tokenizer converts the text into tokens, with a maximum length of 1024 tokens and returns PyTorch tensors. And the truncation ensures that the text does not exceed the maximum length. Finally, we generate the summary from the tokenized input and decode it to get a readable summary. We use the model.generate method to create a summary, using beam search =4 for better quality, with a maximum summary length of 128 tokens and early_stopping to true to finish early if the summary is complete. The tokenizer.decode method converts the token IDs back to a human-readable string, skipping any special tokens used internally by the model. We print the generated summary. In this example, we demonstrated how to fetch a real-world news article, extract its text, and summarize it using the BERT model. The process involves loading the BERT model and tokenizer, fetching and parsing the article content from a news website, tokenizing the text, generating a summary, and then printing the summarized text. This approach showcases the practical use of transformers in NLP tasks like text summarization, providing concise summaries of lengthy articles. Let us now look into our second case study of text classification. Text classification is one of the fundamental tasks in natural language processing, NLP, where the goal is to assign predefined categories to text documents. In this section, we will explore how to implement transformers for text classification tasks using the HuggingFace Transformers library. We will provide code example and analyze the performance of the model. So, first look into the implementing transformers for text classification. The transformers, such as BERT, have been highly successful in text classification due to their ability to understand context and handle long-range dependencies. Here is a step-by-step guide to implementing a transformer model for text classification. Step 1. Prepare the dataset. Collect a labeled dataset suitable for text classification. For this example, we will use the IMDb Movie Reviews dataset, which contains movie reviews labeled as positive or negative. Step 2. Loading the pre-trained model and tokenizer. We will use a pre-trained BERT model and its corresponding tokenizer from the HuggingFace Model Hub. Step 3. Tokenize the text data to convert it into a format that can be fed into the BERT model. Step 4. Create PyTorch data loader objects to handle batching and shuffling of the dataset. Step 5. Fine-tune the pre-trained BERT model on the text classification dataset. Step 6. Evaluate the model on a validation set and analyze its performance using metrics like accuracy. The step-by-step explanation of the example code. First, you need to install the datasets library and import all the necessary libraries. The datasets library is installed to load the IMDb dataset. And the PyTorch and Transformers libraries are imported for model training and tokenization. Second, load the IMDb dataset, which contains movie reviews and their associated labels, positive or negative. Third, load the pre-trained model and tokenizer. The BERT model and tokenizer are loaded. The model is pre-trained on a large corpus of text and fine-tuned for sequence classification. Fourth, tokenize the dataset. The text data is tokenized into a format suitable for the BERT model. The map function applies tokenization to the entire dataset. The text column is removed, and the label column is renamed to match the model's expected input format. Fifth, reduce dataset size for training and evaluation. The dataset size is reduced to 20 samples for both training and evaluation to make it manageable for low-resource machines. Sixth, create PyTorch data loader objects for training and validation datasets. The data loaders are created for batching and shuffling the dataset during training and evaluation. Seventh, define optimizer and learning rate scheduler. The AtomW optimizer and a learning rate scheduler are set up. The training is limited to 1 epoch and 5 steps to fit within resource constraints. Eighth, move model to GPU. The model is moved to a GPU if available, otherwise, it uses the CPU. Ninth, mixed precision training and training loop with gradient accumulation. Mixed precision training is used to optimize memory usage. The training loop runs for a single epoch and is limited to 5 steps. Each step includes a forward pass, loss calculation, backward pass, and optimizer update. 10th, define evaluation loop. The evaluation loop runs inference on the validation set and calculates the accuracy of the model. The output shows the loss at each step and the accuracy after 1 epoch of training. In summary, implementing transformers for text classification tasks involves loading a pre-trained model, tokenizing the dataset, fine-tuning the model, and evaluating its performance. Transformers like BERT have proven to be highly effective for text classification due to their ability to capture contextual information and handle long-range dependencies. The provided code examples demonstrate the practical steps to implement and fine-tune a transformer model for text classification, showcasing its capabilities and effectiveness in real-world applications. The transformers have revolutionized natural language processing with their ability to handle long-range dependencies and parallelize computations efficiently. Here's a concise summary of their architecture and key components. The transformers consist of an encoder and a decoder. The encoder processes the input sequence and generates a set of continuous representations, while the decoder uses these representations to generate the output sequence. The self-attention mechanism. Both the encoder and decoder utilize self-attention mechanisms to weigh the importance of different tokens in the sequence. In the encoder, the multi-head self-attention allows the model to focus on different parts of the input sequence simultaneously. Each attention head captures different aspects of the input data. The position-wise feed-forward networks consist of two linear transformations with a ReLU activation in between. They process each token independently after the attention mechanism. And the positional encoding adds information about the position of tokens in the sequence to the input embeddings, enabling the model to capture the order of words. And in the decoder, the masked multi-head self-attention ensures that the decoder can only attend to previous positions in the sequence, maintaining the autoregressive property needed for generation tasks. The encoder-decoder attention allows the decoder to focus on relevant parts of the input sequence while generating the output. The position-wise feed-forward networks and the positional encoding. Similar to the encoder, these components are used to process and encode positional information. For the pre-training, the transformers are often pre-trained on large corpora to capture general language representations. And the pre-trained models are fine-tuned on specific tasks using task-specific datasets, making them highly adaptable and efficient for various NLP applications. The variants and innovations in the transformer. The variants like BERT, GPT, and T5 introduce different pre-training objectives and architectures to improve performance on specific tasks. The techniques such as sparse attention, model compression, and distributed training improve the scalability and efficiency of transformers. Having covered the fundamentals and advanced topics related to transformers, here are some next suggested steps for further learning and exploration. Experiment with different datasets. Apply transformers to a variety of NLP tasks using different datasets to gain hands-on experience. Explore advanced architectures. Investigate newer transformer architectures and innovations, such as long-former, reformer, and other models designed for specific tasks. Participate in competitions. Engage in NLP competitions on platforms like Kaggle to test your skills and learn from the community. Contribute to open-source projects and repositories related to transformers and NLP to collaborate with other developers and researchers. Keep up with the latest research papers and advancements in the field of transformers and NLP to stay informed about new developments and techniques. We have also looked into the 2 case studies. In summary, this chapter has provided a comprehensive understanding of transformers, their architecture, components, and applications. By revisiting these key concepts and taking the next steps, you can continue to build on your knowledge and apply transformers to solve real-world NLP problems. In next chapter we will delve deep into multilingual named entity recognition and we will explore how a single transformer model called XLM-RoBERT can be fine-tuned to perform named entity recognition (NER) across several languages. As we saw in Lecture 1, NER is a common NLP task that identifies entities like people, organizations, or locations in text. These entities can be used for various applications such as gaining insights from company documents, augmenting the quality of search engines, or simply building a structured database from a corpus. Thank you for joining us for this lecture. We hope you found the content informative and helpful. If you have enjoyed this video, Please give it a thumbs up, share it with your friends, and don't forget to subscribe to our channel for more educational videos. Your support helps us create more valuable content for you. See you in the next video.